Okay, we're going to go ahead and work through one more example. This is example 3, and I'm going to make this one a little quicker than the last one. I don't have a rational function, although I am seeing a product rule there. Just a quick reminder that our goal is to determine these 4 things. And if you're watching this and you already watched my previous one, example 2, this was from example 2, which was the function x over x squared minus 36. I did make a mistake here that I wanted to point out, and we only have a point of inflection at x equals 0 because x equals -6 and +6 are vertical asymptotes, which I said, and I just messed up when I was writing the point of inflections. They're not defined for the function, and therefore they can't be points of inflection. So it does have to be a point on the graph. Okay, so continuing with this one, let's go ahead and take my derivative. You guys know the drill here. So what I really wanted to do here is work one out that had a product rule and also a chain rule, just as a quick reminder of our derivative rules. So I've got first function times derivative of the second. Please be careful. Derivative of e to any power is e to that power times derivative of that power. Derivative of x to the 6th, so I really have x over 6. I prefer to write that as 1/6 times x, so my du is going to be 1/6. So that's the first part of my product rule, first times derivative. Second, plus second, which is e to the x over 6, times derivative of the first, which is 1. I'm just going to tidy things up a little bit. And let's go ahead and rewrite that. If I can factor something out, I'm going to have to set this equal to 0. So I am seeing that I have e to the x over 6 in both terms. Let's factor that out, and then I get 1/6 x plus 1. And then I'm going to go ahead and evaluate. When's that going to be equal to 0? When's that going to be undefined? Let's find our potential critical points. So I'm going to set e to the, since it's already in factored form, let's just set this equal to 0. And I'm going to say 0 is equal to e to the x over 6, or 0 could be 1/6 x plus 1. That'd be -1 is equal to 1/6 x. Times 6 on both sides gives you a -6 for x. And then on the other side, I'm going to take the natural log of both sides. Natural log of 0 is not defined. That's undefined. So therefore, I'm going to get no real solutions for that part. So there is no place where this is going to be undefined. X can be anything. So I'm going to go ahead and say we're done with critical points, and I only got one critical point right here. So maybe this one won't be quite as bad. Let's go ahead and make our number line analysis. So here's my number line analysis, and all I have so far on it is a -6. My first derivative is equal to 0 at that point, and now I'm going to do my test values. So I'm going back over here, and my test values, I need something lower than -6 and something higher than -6. So I'm going to test -7, and then I'm going to test 0. So if I'm testing -7, I'm going right to this factored form here. So e to the -7 over 6. Now you really got to think about this. I'm trying to do this without my calculator. E to the -7 over 6 is really, remember, negative power just drops it to the denominator. So it's 1 over e to the 7 over 6. But that's still going to be positive. So all I care about is signs. That's going to be positive. And then I've got 1/6 times -7. That's -7/6 plus 1 is going to be a negative, giving me a negative. And then if I plug in 0, this one's going to be a little easier. E to the 0 is 1. So that's a positive times 0 makes that term go away plus 1. And I've got a positive there, giving me a positive. So it looks like I've got a negative and then a positive, meaning my function is roughly decreasing and then increasing. So let's see if we can figure out the curvature and what it's doing more specifically. So of course we're going to look to our second derivative. So second derivative, and I suppose I am going to use this, the one that I've got highlighted in yellow here to do my second derivative, because I've got a product rule, but it seems a little simpler than the what's above it that has a product rule and a sum plus another one. So let's go ahead and go from that and work out our second derivative. So second derivative is equal to first function times derivative of the second, which is 1/6, plus second function, which is 1/6 x plus 1, times derivative of the first, which is e to the x over 6 times 1/6. Let's see if I can tidy that up. So that's going to be, I'm seeing that I have an e to the x over 6 and a 1/6 in both terms. So I'm going to pull out 1/6 times e to the x over 6. And I'm seeing I've got two functions, so notice your plus sign. I just pulled out that entire thing, and I've got that here. So really all I've got left inside then is 1 for my first term here, plus this came out, so I've got the 1/6 x plus 1 left in parentheses. And I think I can simplify that. So let's go ahead and simplify that, and that's giving me 1/6 e to the x over 6 times 1 plus 1 is 2, so I've got 1/6 x plus 2. And I think we'll call that good. So I'm setting that equal to 0 to find my potential points of inflection for where my second derivative is equal to 0 or undefined. So I've got 0 is equal to 1/6 times e to the x over 6, and then 0 is equal to 1/6 x plus 2. Negative 2 equals 1/6 x multiplied by 2, and I get negative 12 for one of my values of x. And then I'm taking the natural log of both sides here to get my variable. Actually, I take that back. 0 equals 1/6 e. I would multiply by 6 on both sides first to get 0 equals e to the x over 6. Now take the natural log. Natural log of 0 is undefined, so I've got no real solutions over there. So I just have one critical point of my second derivative, which is negative 12. So I'm going to put that on here. Negative 12 is, of course, over here. So I've got second derivative is equal to 0 at negative 12. And I've got to test two intervals, and that would be less than negative 12, greater than negative 12. I should have maybe written in here that I have decreasing and increasing function, just to emphasize that point. Okay, so let's test some values here. So going down to here, test values, I am using this factored form, and I'm going to test f double prime of negative 13 and f double prime of 0. So 0 first, let's do that one. E to the 0 is 1, so I've got positive out front there, and then I've got 1/6 times 0 plus 2 is giving me a positive, overall. Negative 13, so negative 13 over 6, again, this e to the negative 13 over 6 is going to be 1 over e to the positive 13 over 6, which is a positive number. It's going to be a super small number, but that's a positive. And then 1/6 times negative 13, this is going to be negative 13 over 6, plus 2 is going to be a negative. So I do have a negative in there, giving me a negative overall. So I've got negative and positive for my signs. So negative and positive, that gives me concave up and then concave down for that entire interval. So that's just to negative 12. So on this decreasing part here, I'm going to have concave down, and then I'm going to have concave up, and it's going to continue concave up for the rest of it, all the way from negative 12 all the way through to positive infinity. So I would encourage you to take a look at your calculator. I'm not going to take the time right now to graph it in the calculator, but please take a look in your calculator and see if that matches up with what you're seeing in your calculator. Just to write up my answers, let's see if I can do a better job this time. Increasing would be on negative 6 to infinity, and then it was decreasing on negative infinity to negative 6. Relative minimum this time. So I do see a minimum right here. I I should say at this x value -6 because my derivative is changing signs from negative to positive, versus the other one I didn't have a change in sign in my derivative. So minimum at x equals -6, if we wanted to find the y value, we could do that. No relative max. So that was B. C is concave up. And concave down. And then D is points of inflection. Would be change in the second derivative sign, which is at x equals -12. That is actually a point on the graph. So I'm good to go with that.